Recently, astronomers made a groundbreaking discovery by pointing the powerful Keck telescope in Hawaii at what seemed like empty space. Their goal was to explore beyond what had previously been observed and uncover the hidden secrets of the cosmos. They found something extraordinary, a vast halo of gas surrounding galaxies, stretching over 100,000 light-years beyond their visible edges. In this video, we'll dive into what these enormous gas halos are, the cutting-edge technology that made their discovery possible, and why this finding could revolutionize our understanding of galaxy formation and the cosmic web. Galaxies are much more than the bright stars we see dotting the night sky. Surrounding each galaxy is a colossal shroud of gas, known as a galactic halo, that extends far beyond the visible boundaries of the galaxy. Recent observations have shown that these halos are more massive and far-reaching than we once believed. Composed mainly of hydrogen, helium, carbon, nitrogen, and oxygen, these halos stretch over 100,000 light-years, which almost equals the distance from our Milky Way to the Andromeda Galaxy. The significance of these halos lies in their vast amount of matter. Studies estimate that these halos contain between 70% to 90% of the universe's normal or baryonic matter. This means that most of the universe's ordinary matter isn't in the bright stars, planets, or even the galaxies themselves, but in these immense, diffuse clouds of gas, which dramatically changes our understanding of where the bulk of the stuff in the universe actually resides. Instead of being confined to the luminous stars and galaxies that we can see, most of it is hidden away in these nearly invisible halos that stretch across the cosmos. However, these halos are not just simple static clouds. Recent findings reveal that the boundary between a galaxy and its halo is not a gradual fade as once assumed, but rather an abrupt transition. This sharp boundary suggests that the processes within these halos are far more complex and dynamic than we previously imagined. Some areas within the halos may have denser concentrations of certain elements, while others might be almost completely void. This diversity likely reflects a complicated history of galactic winds, gas inflows, and outflows that have shaped the halo over billions of years. These halos are crucial to galaxy formation, because they serve as vast reservoirs of material from which galaxies draw to form stars and planets. When gas within a halo cools and condenses, it can fall into the galaxy, sparking the birth of new stars. Conversely, powerful events like supernovae can expel gas from a galaxy back into the halo, creating a cyclical exchange of matter that is essential to a galaxy's growth and evolution. This dynamic makes halos not just passive structures surrounding galaxies, but active participants in the cosmic cycle of creation and destruction. While visualizing these gas halos is a significant achievement, many questions remain, particularly about why these halos glow and what governs their interactions and properties. Unlike the dense regions within galaxies, where the glow of hydrogen gas is typically caused by strong radiation from nearby stars, the vast expanses of a halo lack sufficient stellar radiation to account for their faint light. So, what makes these halos emit light? One leading theory is that gas streams within the halos collide at high speeds, generating shock waves that cause the gas to glow. These collisions could produce enough energy to make the gas shine, even in regions where there is insufficient stellar radiation. This theory suggests that halos are not uniform structures, but rather dynamic and turbulent, filled with streams of gas moving in different directions and colliding like cosmic rivers. Such collisions could play a significant role in how galaxies draw in gas to form new stars or expel it back into intergalactic space. Another possibility involves ultraviolet light from massive stars or black holes within galaxies. Some of this UV light can escape into the circumgalactic medium, CGM, and create an ambient cosmic background that interacts with the gas in the halos. When combined with fast-moving gas streams, this UV background might be enough to produce the faint glow observed in the halos. However, this idea requires more evidence to determine how much UV light escapes from galaxies and how it influences the surrounding gas. Recent studies have also revealed that the CGM is not heated uniformly. Within galaxies, stars ionize gas with their photons. But in the CGM, gas is heated by more diffuse sources, possibly including emissions from numerous galaxies or intergalactic shocks. This uneven heating changes the physical conditions of the gas, creating a distinct boundary between a galaxy's interstellar medium and its circumgalactic medium. These clear distinctions, observed in recent research, help refine our understanding of where a galaxy's influence fades and where it merges into the broader cosmic web. Moreover, the latest observations have identified that the CGM could be shaped by various elements like hydrogen and oxygen, which extend from the center of the galaxy far into space. These elements are not uniformly distributed. Their presence varies with distance, indicating ongoing processes that alter the chemical composition of the halos. This raises intriguing questions about the interactions between galactic halos, particularly those of the Milky Way and Andromeda. Given that the Milky Way's halo extends about 100,000 light-years, it is likely already overlapping with Andromeda's halo. This potential overlap suggests that the circumgalactic mediums, CGMs, of these two galaxies are beginning to interact, revealing more complex intergalactic dynamics than previously understood. Studying these overlapping halos could provide valuable insights into the processes that may lead to a future merger of the Milky Way and Andromeda. The discovery of these enormous halos was made possible by the Keck Cosmic Web Imager. This sophisticated instrument uses a new type of spectrograph called an image slicer, which allows astronomers to capture spectroscopic images of extremely faint regions of the night sky, something beyond the reach of previous technology. The Keck telescope, one of the largest optical telescopes in the world, is ideally positioned atop the Mauna Kea volcano in Hawaii. The site's high altitude, clear skies, and minimal light pollution make it one of the best locations for astronomical observations. The imager leverages this optimal environment and its ultra-sensitive imaging capabilities to detect incredibly faint light from gas that is tens of thousands of times dimmer than the bright parts of galaxies. This sensitivity is crucial for studying gas halos, which are notoriously difficult to observe due to their diffuse nature and the vast areas they occupy. This kind of observation pushes the limits of current technology, but thanks to astronomers like Nikki Nielsen and her team, who carefully analyzed the data, we now have the first detailed image of a galactic halo. This breakthrough has provided a new window into the universe, allowing scientists to explore the unseen structures that play a vital role in galaxy formation and evolution. Building on these findings, the James Webb Space Telescope is set to explore halos and other faint cosmic phenomena further. With its capability to observe in the infrared spectrum, Webb will provide complementary data, potentially revealing more about the chemical composition and temperature variations within these halos.